Assalamualaikum and hi everybody. In this video, I will continue with the introduction topic for Chapter 4 on Tests of Hypotheses in Engineering Statistics SSCE2193 course. In this second part of the introduction topic, we will focus on the topic's third learning objective, which is defining the type of statistical errors which can occur when we perform a statistical hypothesis test. In addition, we'll also look at the common procedure of a hypothesis test, which is the topic's last learning objective. Let's proceed to the next slide. You can refer to page 84 in Statistics for Engineers textbook for the type of statistical errors we can possibly make when we perform a test of hypothesis. There are two possible errors that can occur in a test of hypothesis as tabulated in this table. Let me explain the table. The first column shows two possible states of nature. Either H0 is true or H0 is false, which implies H1 is true. The state of nature is the actual behavior or situation of the parameter that we want to test. Usually, this state of nature is unknown. That is why we want to carry out a hypothesis test. When we carry out a statistical testing, what we do first is collecting some information from sample data. Based on the sample data or sample information, we will eventually come to a decision or conclusion about H0 as listed in the first row. The conclusion could either be reject H0, that is H0 is false, which implies H1 is true, or the conclusion could be do not reject H0, that is H0 is true. If the conclusion we make tallies with the actual state of nature, then we make a correct decision. For example, if H0 is true by nature, and after doing a statistical testing, we conclude to accept H0 or do not reject H0, we then make a correct decision. Similarly, if by the state of nature H0 is false and our conclusion is to reject H0, we again make a correct decision, since our conclusion tallies with the state of nature. However, if the state of nature H0 is true, but somehow we have evidence from the sample data to reject H0, here our conclusion does not tally with the state of nature, we are then said to make a type 1 error, which is defined as rejecting H0 when H0 is true. Likewise, if the state of nature H0 is false, that is, H1 is true, but after running a statistical test, we conclude to accept H0. In this case, we are said to make a type 2 error, which is defined as accepting H0 when H0 is false. In the previous slide, we have looked at how type 1 and type 2 errors were defined. Let's look at the definition again. Type 1 error is when we reject H0 when H0 is in fact true, whereas type 2 error is when we accept or we do not reject H0 when H0 is false. How do we measure how much the errors have occurred in a hypothesis test? That is, how to quantify the errors. The answer is through probability. We can quantify type 1 error by finding the probability of making type 1 error, denoted by alpha. Here alpha is the level of significance at which we run a test. For this course, students are expected to only know that the level of significance alpha can also be used to quantify type 1 error. What about type 2 error? How do you quantify the type 2 error? We can quantify type 2 error by finding the probability of making type 2 error denoted by beta, whereas 1 minus beta is gamma, which denotes the power of test. Please be informed that the calculation of beta and the calculation of gamma are not covered in this engineering statistics course. Nevertheless, an important point to note is that when we reduce alpha, beta would increase. On the other hand, when we reduce beta, alpha will increase. The next question to figure out is how to reduce alpha and beta at the same time. Some references suggest that you may increase the sample size to reduce alpha and beta in a statistical testing at the same time. This is an interesting topic covered not in this course but at an advanced level of a statistical course. This slide shows a conventional hypothesis test procedure which can be applied to any test of hypothesis not only from chapter 4 but also from other chapters like chapter 5, 6 and the last chapter in this course, which is chapter 7. Let's look at the procedure step by step. The first step is to identify which parameter we want to test. Remember, in this chapter, we only focus on 6 parameters, which are mu, pi, sigma squared or sigma, mu1 minus mu2, pi1 minus pi2, or the ratio of population variances sigma 1 squared over sigma 2 squared, or the ratio of two population standard deviations sigma 1 over sigma 2. Please remember that we do not test sample statistics such as x bar, p, or s squared. So identify correctly which of the 6 population parameters to be tested. That's the first step. The second step is to formulate H0 and H1. Remember the style of writing this hypothesis. The rule is that under H0 you always have equality sign, whereas under H1 you could have one of the 3 alternative hypotheses that I already discussed in the first part of this introduction topic. Are you testing a difference in theta value? That is a two-sided alternative hypothesis which involve an unequal sign under H1. Are you testing an increase in theta value? That will be a right-sided alternative hypothesis which involve a greater than sign under H1. Are you testing a decrease in theta value? That will be a left-sided alternative hypothesis which involve a less than sign under H1. Can you follow? If not, please watch the video on the first part of this introduction topic again. Now the third step. Choose or identify the level of significance alpha at which you will carry out the statistical test. For this course, usually alpha value will be given. However, if you were to carry out your own statistical hypothesis test, then you need to decide or identify the alpha value before performing the statistical test. The other 3 steps will be discussed in the next slide. We continue with the other 3 steps in a hypothesis test procedure in this slide. The fourth step is determine the distribution and state the rejection region of the specified test statistic. That is, establish a decision rule or test criterion by writing reject H0 if the test statistic is less or greater than a critical value. At this step, you should identify which test statistic to be used in a hypothesis test. For example, If you test a population mean mu, you can either use a z-test statistic or a t-test statistic. If you test a population variance, sigma squared, or population standard deviation, sigma, you will use a chi-square test statistic, and so on. Having identified the correct test statistic, you can then write the decision rule, which follows what you specify under the alternative hypothesis H1. For example, if you have a right-sided test, then your decision rule will be reject H0 if the test statistic is greater than the critical value at alpha on the right. If you have a left-sided test, then your decision rule will be reject H0 if the test statistic is less than a critical value at alpha on the left. However, if you have a two-sided test, then your decision rule will be reject H0 if the test statistic is less than a left critical value at alpha over 2, or if the test statistic is greater than a right critical value at alpha over 2. Please watch the first video again for clear illustrations. Now the fifth step. Calculate the test statistic that you have identified in step 4 earlier. The calculation of the test statistic is based on the information from random sample, where the data from random sample has been collected earlier, and by assuming that H0 is true. That's why under H0 we always have the equality sign so that we can use the parameter value under H0 to calculate the test statistic. The last final step in this hypothesis test procedure is to make decision and conclusion based on the comparison between test statistic and the critical value. If the test statistic falls in a critical region, then we can decide to reject H0 in favor of H1. Otherwise, if the test statistic falls in the acceptance region, we do not reject H0. Decision is usually on deciding whether to reject or not to reject H0. However, the final conclusion must be provided, which should practically answer the problem or question related to the parameter being tested. You will understand this final step better when we do some real and practical problems in the later topics. Before we go into detail on testing each and individual population parameter covered in this chapter, let us look again at the list of parameters we are going to test in this chapter. As I mentioned earlier, there are 6 population parameters we will explore in this chapter. Remember, we use Greek letters to denote the population parameters. The 6 parameters are exactly the same parameters we have estimated in Chapter 3 on estimation. The parameters to be tested include the parameters from single populations, which are single population mean mu, single population proportion pi, and single population variance sigma squared or standard deviation sigma. Furthermore, the parameters covered in this chapter also include those from 2 populations, which are the difference in 2 population means mu1 minus mu2, the difference between 2 population proportions pi1 minus pi2, and the ratio of 2 population variances sigma 1 squared over sigma 2 squared, or the ratio of 2 population standard deviations sigma 1 over sigma 2. The corresponding choice of test statistics and the critical values are listed as follows. For testing mu, we will have either Z or T test statistics, which will be respectively compared with Z or T critical values before making a decision to reject or accept H0. Similar to Chapter 3, we have 3 cases in testing mu. Next, we have 5 cases in testing mu1 minus mu2. Again, we can either have a Z or T test statistic and the corresponding critical values. Next, only one case for testing a single pi, which is using a Z test statistic to be compared with a Z critical value. Next, we have 2 cases for testing pi1 minus pi2, where both cases will use Z test statistic, which is to be compared with a Z critical value. Similar to estimation chapter, we only have one case in testing sigma or sigma squared, that is a chi-square test statistic, which is to be compared with a chi-square critical value. The last parameter of interest in this chapter is testing the ratio of sigma 1 squared over sigma 2 squared, or the ratio of two standard deviations, sigma 1 over sigma 2. Here, we only have one case, that is to use an F-test statistic that will be compared with 1 or 2 F critical values. What is the connection between confidence interval we learned in Chapter 3 on estimation and the test of hypothesis in Chapter 4 right now? Since we dealt with a two-sided confidence interval in Chapter 3, we can actually see the connection through a two-sided hypothesis test. Now suppose a two-sided 100 times 1 minus alpha % confidence interval for a population parameter theta is LU, where L is a lower limit and U is an upper limit of the confidence interval, then at alpha % level of significance, we will certainly reject H0 theta equal to theta naught in favor of H1 theta not equal to theta naught if and only if the confidence interval LU does not contain theta naught. For example, if an interval 611 is a 95% confidence interval for a population mean mu, then at 5% level of significance, we will certainly reject H0 mu equal to mu naught if and only if mu naught is not in the 95% confidence interval 6 and 11. Let's say mu naught is 12. Then we will reject H0 at 5% level of significance because the confidence interval 611 does not contain the value 12. However, if mu naught is 9, say, then we will not reject H0 because the confidence interval 611 contains the value 9. So that is the connection. Although confidence interval and test of hypothesis have a connection between one another, as seen in the previous slide, of course, these both statistical inferential approaches have different insights. On one hand, a confidence interval actually provides a range of likely values for a parameter at a stated confidence level. On the other hand, a hypothesis test actually provides a framework for displaying the risk levels associated with a specific decision. We are at the end of introduction topic. Before ending this session, let's do a checklist on this topic's learning objectives. After going through the 2 videos on this introduction topic, are you now able to recognize the common terms in the test of hypothesis? Please be familiar with all the important terms as you'll be using the terms very often until the end of this engineering statistics course. What about the second learning objective? Are you now able to identify different types of hypothesis tests? This learning objective is crucially important to remarkably master this chapter. What about the third learning objective? Are you now able to define the two types of errors that could occur in a statistical testing and detect at least the probability of making type 1 error? You should at least know what type 1 error is and its corresponding probability, which is simply the level of significance alpha. Finally, are you now able to list down the important steps in a common hypothesis procedure? If you have some doubts, please watch again the two videos and highlight the doubtful arguments or explanation for further clarification during our discussion. Please make sure you achieve all the introduction topics learning objectives before we go into detail on testing each of the 6 parameters one by one in other sessions. For the time being, thank you very much for watching. Assalamualaikum and see you again in other videos. Take care and bye for now.